Euler and Hamiltonian circuits and paths. This is section 5 in your text. Just a quick run through of basically what it talks about. We're not going to go into too much detail in this video, just because a lot of the theorems are pretty self-explanatory, and really you just need to work with the information that we're about to discuss. First off, an Euler circuit or path will cross each edge exactly once. If it's helpful to remember, you can always remember Euler starts with an E, edge starts with an E. And then the Hamiltonian path or circuit will cross through each vertex exactly once. Key being the word exactly. In other words, it doesn't cross the same vertex more than once. Problems in which these types of paths or circuits might come up. You can imagine snowplow. If you're trying to find the most efficient route to plow some streets in which the vertices are intersections of the streets and your edges are the streets themselves. Okay. So if you're looking for the most efficient snow plowing route, you're going to try to find an Euler path or an Euler circuit in which you can cross each street exactly once without doubling up, thereby eliminating wasted gas and wasted time. That's one of the more simple examples for an Euler path, an Euler circuit. Hamiltonian path circuit, the classic example is the traveling salesman problem, which we'll get to in much more in the next section. Traveling salesman problem, or TSP. But essentially, traveling salesman problem, you're asking yourself how you can get between different stops or cities without having to go to the same city more than once. Okay. Oftentimes we're going to be looking at a Hamiltonian circuit just because, well, we're going to start in one place and we want to end in that place as well. So with the traveling salesman problem, we're looking at vertices, not edges, that we want to travel to exactly once. And those vertices for this problem are going to be the cities, or those sales calls, if you will. With regards to edges on the traveling salesman problem, it's not a big concern, mostly because it just depends on how you want to travel for that particular problem, but it's going to be the traveling between the cities. We'll be talking about a weighted graph here coming up, and that's more designed for the traveling salesman problem, but that's a general idea right there. Now, when do these exist in a graph? Now, an Euler circuit's pretty simple. It exists only when all vertices are of even degree. All vertices, even degree. Okay. All vertices have to be even degree. If there's even one odd vertex, then no Euler circuit exists. An Euler path is similar, but there can be at most 2 odd vertices. Oops, 2 odd vertices. Okay, so for an Euler circuit, we need no odd vertices. For an Euler path, we can have no more than 2 odd vertices. And for a Hamiltonian circuit, it gets a little more complicated. First of all, a Hamiltonian path is usually fairly simple to come up with. Path in which we cross through each vertex exactly once. So we don't usually discuss this. It's also not as interesting for us, but the Hamiltonian circuit has a few more theorems about it and a few more options. First of all, in your textbook, I think the first one is theorem 3, which is Dirac's theorem. And that states that if G is a simple graph with n vertices, where n is greater than or equal to 3, with degree of every vertex in G at least n over 2. So each vertex with degree greater than or equal to n over 2. If that's the case, then that graph has Hamiltonian circuit. And then theorem 4, as listed in your text, which is Orr's theorem, has the exact same hypothesis, but so in other words, we've got a simple graph with n vertices with the added hypothesis that for every u and v or as part of the graph for all vertices in the graph non-adjacent for all non-adjacent vertices, the degree of u plus the degree of v must be greater than or equal to n. Okay. If this is true for all non-adjacent vertices in your graph, then a Hamiltonian circuit exists in that graph as well. Section 6 in your text, shortest path problems. Just a few things to go over here, mostly about traveling salesman type problems is what we're going to focus on here. But first of all, a weighted graph is going to be one like you see down here, in which usually the edges, sometimes the vertices, but usually the edges are assigned weights or values. Now in this case, these weights or these values could be anything from some form of a cost to get from A to B or B to A, or a form of a distance. Okay, whatever is important to you, that's going to be the value that's assigned for the particular problem. But it's all going to be determined in the context of the problem. A path length, then, is the sum of the weights along edges of a path. Okay, so if we're going to go from A to C through B, then that path has length 5 plus 6. So A, B, C has length 11, whereas A to C has length 8. Okay, I know it's difficult to see, but length 8 for the path from A to C. So the shortest path in this case would not be to go from A to B to C, but rather A directly to C. Okay, an alternative path, if we say had to go through at least one vertex to get from A to C, we could go either A to B to C, or A D C, or A E C. All three of those would get us from A to C through one other vertex. Okay. The question would be now, which of these is the shorter path? Okay. This is just how I usually write these. It doesn't matter though. A to B has length 5. B to C has length 6. So this path has length 11. A to D has length 6. D to C length 3. So total length is 9. And finally A to E is 10. And E to C is 2. So this has length 2. So the shortest path through one other vertex from A to C would be the path A, D, C. Okay. Now, this gives you an idea too for why traveling salesman problems or these shortest path problems can be long and tedious, is because the only way to determine exactly which path is the best is by writing them all out. So if we have a complete graph, in this case with 5 vertices, we can find so many different paths between, well, so many different Hamiltonian circuits, say starting at A and ending at A, that we could actually write it out. It's just going to take a while. But the idea is as those vertices increase, then obviously the number of paths, potential circuits, increases, and the fact that we would have to check all of those to be 100% sure that we have the shortest possible path would be extremely inefficient and in some cases take years even on computers. So the book does a good job detailing that, but this is just a quick example of how that works. Of course, the traveling salesman problem would say what is the shortest path, or what is the shortest circuit? Starting and ending at A. Okay. Now, as far as computers are concerned, and the book does a wonderful job explaining it, but we can use this algorithm. I'm sorry, I'm not even going to try to pronounce the gentleman's name, but we can use that algorithm to come up with the shortest circuit starting and ending at A. Another way to do it, kind of a simple way, is just to start at A and take, if you will, the path of least resistance. Right? Water flows through the path of least resistance. We can work the same way. In this case, if we start at A, from A, the closest path, or the one with the smallest weight, is not E, not D. This has weight 10, 6, 8 to C, but length 5 to B. So starting at A, we're first going to go to B, which has length 5. Then from B, I look at the remaining vertices. I've got 3 units to get from B to E, 4 B to D, and 6 B to C. So it looks like I'm going, B to E, because that's only 3 units away. Now I'm at E, I have to travel to D and C. You can see where it's going. E takes 2 units to get to C, 5 to get to D. So we'll go to C. Finally, we have to go to D and then back to A. And this will often give you a shorter path. Okay? This simple algorithm will give you a shorter path, but not the shortest. Okay? Of course, the path length here, 8, 10, 19, would be the length of that path, that circuit. But that's just one way to go about finding a short path. All right, planar graphs. This is section 7 in your text. First off, a planar graph is just one which can be drawn on a plane with no crossed edges. That's right here. This is an example of a planar graph. First of all, it is a planar graph despite being drawn with crossed edges. Note where these edges cross here, here, and here, that there is still, there's no vertex there. So we consider these crossed. For example, one over another. Okay, you can envision a highway overpass where this edge from A to D is an underpass of E to B, right? So B to E is on top of A to D. Okay, a planar graph is one that can be taken from that overpass situation and drawn, say, on a flat surface, okay, on a plane. Notice this is the exact same graph as over here. C is connected to B and D. E is connected to B and D. And so is A, connected to B and D. Of course, you can do the same with B and D and realize that, in fact, this is the exact same graph, just drawn a little bit differently. Remember, with graph theory, space does not matter, except for when we're placing a weighted graph together. Of course, then you have weights here. We have no weights. Okay, we could have weights on a planar graph, that's not a problem, but regardless, this is just an expression of the situation. It's not supposed to show a situation or whatever we're talking about exactly. Okay, again, that's an example used in the text. If we were to view A, B, C, D, and E as different cities with highways that have to go between them, then these overpasses may be a lot more expensive than drawing it without overpasses. Okay. Now we should still be able to draw all of these connections without actually having to cross anything. For example, just redrawing some of these lines, I can go, well, let's do it over here. Okay. We've got C, 2, B, and D. Again, if we're talking about cities here, we don't want overpasses, but we certainly can't move the cities. So we should be able to draw this as a planar graph without actually having to move any cities. Excuse me, if we do so, then I need to connect E and D, as well as E to B. We'll go around C. And finally, the only other connections I need are A to B and A to D. Now, how can I get from A to D? Well, I can either go around here or around here. Either one is acceptable. We're not moving cities, but we're also not creating any overpasses. Okay. So another example of a planar version of this graph, or this planar graph drawn on the plane. Okay. Either of these, of course, are acceptable. This one a little more clear as far as the regions are concerned. A region is simply a space that's broken up by the edges. So in this case, we can see that region R1, R2, and R3 are each distinct. Region R1 is enclosed between these edges. R2 is enclosed between these edges, and R3, of course, is the outside. Okay. Now, we have degrees of edges. Degrees of regions. Each region has a degree, which is essentially the number of edges that make up boundaries. So the degree of R1 just the number of edges that make up boundaries for R1. We've got 1, 2, 3, 4 edges as boundaries for R1. Degree for R2. 1, 2, 3, 4 edges. And this happens to be the degree for R3 as well. Now those outermost edges can be a little bit more complicated, but again, if we were to view this in a slightly different manner, like over here, this is now R1 out here, R2, and R3, and we can see that R3 has 1, 2, 3, 4 edges bordering it. So the outside one could be a little bit more complicated, but it's essentially the edges on the outside of the figure. There's another way you can look at it, or whatever figure is produced by that graph. Okay. So we've got planar graphs can be taken from this version with cross edges to be drawn on the plane where no edges cross. This, we can easily see the regions that the planar graph breaks the plane into. 1, 2, 3 regions. And we can talk about degrees for each of those regions. Euler's formula is about the most important formula. There's a bunch of corollaries in the textbook. I'm not too concerned with you memorizing any, let alone all of those corollaries as far as those numbers are concerned. But this is a very useful formula that the regions for a planar graph are going to be equal to the number of edges minus vertices plus 2. So in this case, we can see we have 3 regions. That should be equal to the number of edges, 1, 2, 3, 4, 5, 6, minus the number of vertices, there's 5, plus 2. And indeed, 1 plus 2 is 3. It checks out. Okay, so that's one way you can also check yourself to make sure you've got the proper number of regions. Most common mistake you can imagine here is to neglect this outside region, in this case R3. Okay, so that's one way you can double check yourself fairly quickly. It's just to make sure that that outside region is accounted for. Okay. Last big definition we've got are homeomorphic graphs. Okay. A homeomorphic graph can be obtained from, or homeomorphic graphs, two graphs can be obtained from the same graph through elementary subdivisions are considered homeomorphic. An elementary subdivision is nothing more than taking these two vertices with an edge in between and making them two edges with an added vertex in between them. Okay, so that's an elementary subdivision. We're dividing this edge into two separate edges. Okay, homeomorphic graphs require a little bit more thought, mostly because this graph is exactly the same as this graph, and the homeomorphic graphs you have to look a little bit harder. For example, a graph that's homeomorphic to this one would be this graph. Okay. This graph is homeomorphic to this one because if you take this one and perform one elementary subdivision, you get this one. Okay, so these graphs are homeomorphic. Okay. Of course, you can continue that process to get smaller and smaller graphs, but that's the basic idea here, is through elementary subdivisions we can create smaller and smaller graphs. Okay. And here, note as well that there's three regions for this graph. 1, 2, 3. And if we subtract the number of vertices from the number of edges, we have 1, 2, 3, 4, 5 edges. 1, 2, 3, 4 vertices. 5 minus 4 is 1 plus 2 gives us still the 1, 2, 3 regions involved. Okay. So Euler's formula still holds through that elementary subdivision. And finally, the most important theorem from this section is it's going to answer the question, when is a graph planar and when is it not? And a graph is non-planar, not planar, if and only if it contains a subgraph which is homeomorphic to K33 or K5. Of course, K5, traveling salesman problem that we saw earlier. K33, example in the textbook. Just draw it real quick as well. Looks like that. Okay, looks like a heck of a cluster right here. Of course, if you spread it out, it makes a little bit more sense. But K33 and K5 are the two graphs which, well, those two graphs are non-planar essentially. And so any graph that is homeomorphic to those or has a subgraph which is homeomorphic to those is also non-planar. Graph coloring. This is section 8 in your text. It's very simple, nothing very complicated about it at all, but there's one distinction that needs to be made which is not entirely clear in some of the text. So I wanted to go ahead and go through that real quick. First of all, a graph coloring itself is an assignment of colors to the vertices of a graph such that no two adjacent vertices are assigned the same color. Chromatic number is the least number of colors needed to completely color a graph, or to perform a coloring. Okay, messed up a little here, but this is the graph that we saw earlier, and we can discuss a coloring of it by doing just that, by coloring some vertices. If I color this one green, then I cannot color either of these three green because they're adjacent to that one. So I have to color these three red, and because I've colored these red, I can't color it red. I could color it a different color, but I might as well use the same color I've already used. So we could have a coloring with, well, theoretically 5 different colors for this graph, but that's not of any interest. What's interesting is the chromatic number, or the least number of colorings possible, or sorry, number of colors needed to completely color the graph, and that chromatic number of this graph is 2. Now, what's most interesting, and again this is me screwing up, what's most interesting about this is the 4-color theorem. Four-color theorem literally states a chromatic number of a planar graph is no greater than 4. Okay, so the chromatic number is less than or equal to 4 for every planar graph. That's what the 4-color theorem says. It has been proven, but it says that basically for any planar graph, the chromatic number is less than or equal to 4. Okay. Now, oftentimes these color theorems are used when discussing maps. A lot of times you can be given a map of, I don't know, a map of a state that's broken up into counties, and then asked to color it using no more than 4 crayons, something along those lines. In this case, if we're given a map like this one, this is some country broken up into states, or some state broken up into counties, whatever it is, and we want to see if we can complete a coloring of this map using different colors. Misconception is to go ahead and just start coloring the map. If we're talking about it mathematically, at least in terms of graph theory, to color this map, we first need to turn that map into a graph. With this graph, we have vertices, which are the states. We'll call it a country, so these are the states. And the edges are the borders between those states. Okay. Notice that this bottom state is not connected to the top state through any edge because it does not share a border with that uppermost state. Okay. Similarly, these two states do not share a border, but this middle state shares a border with every other state. Okay. Now, to go about our coloring, we can go ahead and perform the same process. This one's going to be green, which means that none of these 3 can be green. But what's more is these 3 cannot be the same color because they're all adjacent, because now we have edges in between, unlike these over here. Okay. So these cannot be green, but they cannot be the same color, which means we're already up to 3 colors. Okay. Those will be a different color than green, so I can color this one green again. Then, because these middle 3 have to be at least 2 different colors, I can have red here, and black in the middle. Okay. So it appears as though the chromatic number for this graph is 3. And to check that, we can go ahead and shade in the corresponding map. And there should be no states which border one another that are shaded in the same color, if we've done everything correctly on the graph. Indeed, that is the case. Okay. So with the graph coloring, we're talking about coloring the vertices of the graphs, not the regions in between. A common mistake would be to try to take this and literally put dots on each of these intersections, viewing each of those lines as edges. That's a very common mistake to make, but when we're trying to color a graph, we're looking at the vertices, not the regions in between. Okay, so again, that assumption that people make when trying to color a map is that each of those states represents a region. That is not the case. Each of your states represents a vertex, and we're coloring those vertices, not the regions.